Bismillahirrahmanirrahim. Welcome to the lecture 13 of digital signal processing. I am Mohammad Atif and my registration number is 62010. Today I will tell you about Z transform and transfer function. The Z transform is very important tool in describing and analyzing digital system. It also supports the technique for digital filter design and frequency analysis of digital signal. The Z transform of digital signal is defined as x of z equal to n equal to 0 to infinity x of n z of minus n, where z is complex variable, and here the summation taken from n equal to 0 to infinity. In this equation, all the values of z that makes the summation exist form a regions of convergence. The regions of convergence check whether the system is stable or not. The regions of convergence in the Z transform domain uh, check the stability of the system. Now we have to find the Z transform of the given sequence. We have x of n equal to u of n, it is unit step function. So x of z equal to the Z transform of this is given by 0 to infinity summation 0 to infinity u of n z of minus n, which is equal to 0 to infinity z of minus n. This represents the infinite geometric series, that is 1 plus a square equal to 1 over 1 minus a. So by using the infinite geometric series, we have 1 over 1 minus z minus 1, which is equal to 1 over z. By taking the LCM, we have z over z minus 1. The regions of convergence for this is z greater than 1, and this describes the region of convergence of this example. Now we take the exponential, and now we take the this example where x of n is equal to a of n u of n, and this represents the exponential. The Z transform of this is given by x of z equal to 0 to infinity of n u of n z minus 1. So as u of n is 1, so 0 to infinity of n z minus 1. By taking n common, we have a into z minus 1, and by applying the infinite geometric series, we have 1 over 1 minus a z minus 1, which is equal to z over z minus a, and regions of convergence for this should be z greater than a, and this represents the region of convergence of this example. Now final sequence where x of n minus a and u of n minus 1, where u of n minus 1 is from minus infinity to minus 1, and it is 1. So by applying the limit, we have minus infinity to minus 1. As we know that the infinite geometric series is from 0 to infinity, so we subtract this from 1. So by adding 1 and subtracting 1, we have 1 minus 0 to infinity a minus 1 over z of n, and applying geometric series here, we have 1 minus a over a minus z, which is equal to z over z minus a, and regions of convergence is inside the circle, and it should be z should be less than a. So the last topic of our lecture is transfer function. The Z transform is useful because it allows us to write transfer function of the given system. Consider this equation: y of n plus a1 y minus 1 up to am y n minus 1 equal to b naught x of n plus v1 x minus 1 plus bm x into n minus 1, where x of n and y of n are the input and output of the system respectively, and a and b are the constant coefficients. So by applying Z transform, we have y of z a1 y of z into z minus 1 a of 2 y of z z minus 2 up to a of n y of n, similarly for inputs. So by taking y of z and x of z common from y of z common from this side and x of z from this side, and divide y of z divided by x of z, we have b naught plus b1 z1 bm zm z power minus m1 plus a1 z1 plus a2 z power to a1 z power. We have the transfer function h of z over y of z over x divided x of z. So we have poles and zeros. The zero of a system are those value of z which make the numerator equal to 0. For 0 we have numerator equal to 0, and the poles of a system are those value of z which make the denominator equal to 0, and for pole we have denominator equal to 0. Poles move the system towards infinity, and while the zero move the system towards 0. That's it from today. Thank you very much.